All right, welcome everyone. So excited to have you here with us today for Infiniscope presents Earth's Magnetic Shield, Protection from Natural Hazards. Everyone in this room is already an Infiniscope member, but maybe it's been a little while since you interacted with us, and that's okay. Just a quick reminder of what we offer. We have classroom-ready content, so these are interactive adaptive lessons you can launch directly from our website. We also have enrollment options to help keep track of student enrollments. We also have a virtual field trip creator, that's Torit, and we also have a simplified lesson builder that allows you to build your own adaptive digital lessons. So if you're interested in learning more about any of those, we have an upcoming introduction to Infiniscope on October 22nd. And when I send out the recording for this, I'll also include a link to register for that. All right, and what brings us here today is our speaker. So we have Dr. Cristian Ferradas Alva, who is a research scientist at the Geospace Physics Laboratory at NASA's Goddard Space Flight Center. He is originally from Peru, where he studied physics and then received his PhD in space physics from the University of New Hampshire. His research focuses on the Earth's magnetic field and its interaction with particles from the sun and other areas of space. So with that, I'm going to stop sharing. I'll let him share his screen, and I'll just take this moment to say thank you so much for sharing your time with us today. We're so excited to hear what you have to share with us.
Yeah, thank you so much for the kind invitation as well. It's very nice for me to be able to speak to you all about some of the work that I do, some of my research, which of course is one of my passions, to study space, something I love and that I get to do on a daily basis. So yeah, so thank you all for joining. And as Sina said, today we're going to talk about Earth's magnetic shield and how this represents a protection from natural hazards. So I'm quickly going to show you what's my plan for this talk. Hopefully you can see my screen well. So this is basically my outline for this talk. So today I want to talk to you about Earth's magnetic shield. Maybe some of you already know about this magnetic shield, maybe some of you don't. So I'm going to introduce to you what this shield is. So I'm going to start by explaining what this shield is, and this shield is called the magnetosphere. So I'm going to first talk about the magnetosphere. Next, I'm going to talk about geomagnetic storms. Again, maybe some of you already have heard this term about geomagnetic storms, but we're going to talk a little bit of what they are, what they can do, and how we can know how strong a storm can be. And after that, we're going to go into an activity where you will be able to participate and practice the concepts and the knowledge that I'm going to present before the activity. And finally, we're going to end talking about space weather. So space weather is deeply connected to the two first topics, to the magnetosphere and to geomagnetic storms. So we're going to finish talking about space weather and how different it is from regular weather. Okay, so let's jump in and start talking about the magnetosphere. So first of all, when maybe you hear the magnetosphere, the first thing that comes to mind maybe is the atmosphere, right? Because both words end with sphere. And a lot of people, when I ask them, do you know what the magnetosphere is? Their first answer is, oh, probably it's just one layer of the atmosphere, right? And I have to say, no, actually, the magnetosphere is not one layer of the atmosphere. The magnetosphere is something different and apart from the atmosphere. So to start thinking about the magnetosphere, we have to think about the Earth and one specific property of the Earth, which is that the Earth is like a giant magnet. And what a giant magnet means is that any magnet creates a magnetic field around the magnet. And the Earth really is like a giant magnet. And in this picture here to the right, you can see a side view of the Earth. So we have the Earth here. And we can imagine as if the Earth at its center has this magnet. And the magnet, as I was saying, creates magnetic field lines. And this is what the white lines are in this diagram that I've labeled or called magnetic field lines in 2D, right? Because we're just seeing like the magnetic field lines as if they were in a plane. Uh, Now you can say, "Oh, I've never seen these lines," and you will be absolutely right because these field lines are not visible. We cannot see them. That's why this is just a representation of what these field lines would look like if we were able to see them. Um, Okay, so this is the first property we have to remember when we think of the magnetosphere, that the magnetosphere comes about because the Earth is a giant magnet. And because the Earth is a giant magnet, it has these magnetic field lines, as you can see here in 2 dimensions. But what would they look like in 3 dimensions? So here in this animation here, hopefully you'll be able to see um, the 3D representation of the magnetic field lines. And hopefully you can see this animation. Again, we have the Earth at the center. And then now we can see these field lines. As the Earth rotates, the field lines also move around the Earth. And so these field lines, you can see they surround the Earth all around it, right? Um, Now, what happens with these magnetic field lines is that when everything, that the Earth is not alone in space. Sometimes when we think of outer space, immediately we think that outer space is empty. But actually, that's not true. The Earth is not uh, in empty space, but actually, the sun, which is our closest star, and I'm sure you're all very familiar with the sun, is constantly blowing a wind outward that flows out from the sun and fills all interplanetary space, that fills space. And this wind blowing away from the sun is called the solar wind. And this wind is constantly blowing out from the sun, and this solar wind shapes or reshapes the magnetic field from the Earth, right? So in this picture here, you can see this is just an illustration, right? This is not a real photograph or anything like this. But here on the left, we see the sun, and the sun is blowing outward this solar wind. And this solar wind travels all the way from the sun. And when it reaches the Earth, which is this little ball here to the right, the solar wind interacts with this magnetic field from the Earth. Remember the field lines that you just saw in the previous animation? All of these field lines are reshaped when the solar wind interacts and hits the Earth. And to illustrate that, we have this animation here. Again, we have the Earth here in the center, and the camera is moving away from the Earth in this animation. And now you're going to see these new field lines. These new field lines are the same field lines that you saw in the previous animation, but they, before they were perfectly symmetric around the Earth. But now you can see that they are elongated, and that's because the sun or the solar wind is constantly blowing away from the sun towards the Earth. And when it interacts with the magnetic field from the Earth, it reshapes them, right? So I'm going to let this play again so you can see these reshaped magnetic field lines as they interact with the sun, with the solar wind, right? You can see that towards the sun, these field lines are compressed, and away from the sun, towards this region here, they are elongated, right? Just as if you had a rock in a river, right? And the river is flowing against the rock, right? We have similarly the solar wind blowing against the Earth. So, okay, so let's move on. And so this is the magnetosphere. And now let's talk about geomagnetic storms. So what is a geomagnetic storm? Maybe when you think of a storm, you think of rain and thunder and lightning, and usually we don't want to go out, right? When there's a storm because it's bad weather, right? Similarly, a geomagnetic storm represents bad weather, but bad weather in space. So when we think of a geomagnetic storm, we think of a temporary disturbance of the Earth's magnetosphere. Remember this region that we saw represented by the field lines, right, that are constantly reshaped by the solar wind. Here in this animation, you can see again the Earth at the center, represented by this little circle here. And in these gray lines represent again the magnetic field lines. And all the color around it represents just the number of particles that are in space. As I was saying before, space is not empty, but it's filled with all this solar wind that flows from the sun towards the earth and filling the whole solar system. So you can see that at some point all of this gets red, right? When all of this gets red is when an explosion, for example, from the sun hits the earth and it changes the whole dynamics, the whole shape of this magnetosphere. So that's what we call a geomagnetic storm. Again, a geomagnetic storm, we can think of it as a temporary disturbance of the Earth's magnetosphere caused by a solar wind shock. You have like a shock wave that hits the magnetosphere, represented by the red, and it disturbs the magnetosphere. Okay, so now let's talk a little bit about the magnitude of a geomagnetic storm, because all storms are not the same. Sometimes we have weak storms, sometimes we have really strong storms, and sometimes the solar wind doesn't create a storm, right? So we have different conditions that will determine the strength of a geomagnetic storm. So the magnitude of a geomagnetic storm is going to be determined in part by the strength and the direction of the solar wind's magnetic field. Okay, so I want you to pay attention here to these two characteristics that we are going to care about: the strength and the direction of the solar wind's magnetic field. Okay, so for example, look at this diagram here at the bottom, right? We have the Earth at the center. We have this little magnet just representing that the Earth is like a giant magnet. Then we have these magnetic field lines that you already saw in the previous slides. The magnetic field lines leave this northern magnetic pole, which is right here in the southern geographic pole, and they will flow, these magnetic field lines go this way, and they go back into the opposite pole, okay? And to the left, we have the sun, and the sun is, as you now know, is blowing constantly the solar wind outward. And the solar wind carries a magnetic field as well, which is the magnetic field of the sun. So when this magnetic field from the sun, or the solar wind magnetic field, is pointing northward, like in this diagram here, it does not interact or reconnect with Earth's magnetic field. What does that mean? That when the solar wind has a northward magnetic field like this, all of the particles that come from the sun through the solar wind, they will just be deflected around around the magnetosphere, and they will continue their path around the magnetosphere. So our magnetosphere is very good at shielding the solar wind when the solar wind has a northward magnetic field. Okay, so the impact of such a solar wind is weak. But what happens when the solar wind has a southward magnetic field, right? Again, the direction is important, but also the strength is important. So if the solar wind has a southward pointing magnetic field, this magnetic field will interact or will reconnect with the Earth's magnetic field right here in such a way that this will produce a storm, right? So first requirement for a storm is that the solar wind magnetic field is southward. And also the severity of a storm will be determined by how large this magnetic field is, right? Because remember, the direction is important, but also the strength of the magnetic field. So the more southward or the larger the magnetic field is when the solar wind magnetic field is southward, the stronger the storm will be, right? So in this case here, in this picture here, we have a southward magnetic field from the sun. So this will create a strong impact on the Earth. And this impact will be a geomagnetic storm. Okay. So again, just as a review from this slide about geomagnetic storms, we care about two characteristics of the solar wind magnetic field: the strength and the direction. Going back to my previous slide, if the direction is northward, there will be no storm. But if the direction is southward, we will have a storm. And the severity or the magnitude of the storm will be determined by how large that southward magnetic field is. Okay, so we will stop here and we will transition into our activity. Okay, and I have two activities actually. So we will try to cover both. We'll see how it goes. We'll start with the first one, and we'll see how you guys do with the first one. And then we might consider transitioning to the second one. Okay, that will be the plan. All right. So activity number one is called solar wind magnetic fields impact on the Earth, right? So we already talked about these two characteristics that are important in the solar wind magnetic field, and that will determine what the impact is on the Earth, right? So here you have 6 diagrams that are labeled with letters A, B, C, D, E, and F. And in each diagram, right, we have both the sun and the earth, right, with the magnetosphere around the earth. But we also have these arrows here, and these arrows can have different directions, as you can see, and they also can have different magnitudes, right, which is given by the size of the arrow. As you can see here in this top right corner, there are 3 sizes. The red arrows are small, the green arrows are medium, and the blue arrows are large, okay? So what you have to do is you have to, well, try to order the following solar wind magnetic fields according to how severely they will impact the Earth, right? Um, so maybe you can start by thinking which of these 6 magnetic fields from the Earth, right? Remember the arrows, will most severely affect the Earth. And remember the two characteristics that we care about, right? The direction of the magnetic field and the strength of the magnetic field. So according to these two criteria, uh, try to look at these 6 magnetic fields, and maybe you can start by saying which one do you think will impact the Earth most severely.
So we're going to give you a minute to think about this, and then you can go ahead and put your answers in the chat.
Okay, we see some answers coming through, which is awesome. Yeah, I think most of you are getting it right. So yeah, think of the one that would have the most severe impact on the Earth. Maybe then you can go and think which one do you think will have the least impact on the Earth. And if you're brave, you can order all of them in order of increasing severity. And I see that some of you have done that actually. Some of you have already said which one is the most severe, and some of you have ordered the six of them.
All right, lots of responses rolling in. That's awesome. Do you want to
Mhm.
maybe talk us through what the correct answers are? And I know I'm curious to hear about sort of those ones in the middle. How do we know, the not the most severe or the least severe, but those other directions are interesting. So maybe you could talk us through some of that.
Yeah. Okay. Let's talk this through. Um, so as you can see, there are three magnitudes of the magnetic field, and they do have different directions. And again, we said that both the direction and the magnitude are important, right? That we learned that, first of all, talking about the direction has to be southward, so to have a geomagnetic storm, right? So just scanning all of these cases, looking at just the direction, we can immediately see that all of them are pointing southward to some extent, except for letter E, right? So right away, we can tell that letter E is going to have the least impact on the Earth because it's the only one pointing northward, okay? All right, so discarding E as the least, having the least impact, then all the other five are to some extent pointing southward. So all of them will produce a geomagnetic storm, right? So now the next thing we need to care about is the magnitude, right? And the magnitude is given by the color, right? And the size of the arrows. So first, let's look at, for example, the smallest ones, the two red ones, right? Even though these two, C and D, are red, this one D is not directly pointing southward, but it's pointing southward, but also in at an angle, right? So just because it's not pointing precisely southward, but it has an angle towards south. That means that the southward component of this magnetic field is going to be smaller than this one, than C. So then we know that D is going to have, let's say, the least severe or the weakest geomagnetic storm, followed by C. And then using the same reasoning, then we can compare the next two, which are B and F, right? B is going to have a slightly weaker effect than F. And then finally, A is going to produce the strongest storm because it has the largest magnitude and is pointing directly southward, right? So if we were to order all of these in order of severity, we will have first E because it does not create a geomagnetic storm. Then we will have D, C, B, F, and finally A. All right. So great job to everyone for tackling that activity. So next activity, what do you think, Sina? Should we go into activity number two?
I think maybe just in the interest of time, we'll skip it. But what we
Mm-hmm.
can do is I can send it out with the recording. And so
Mm-hmm.
those who would like to take a look at that second activity, I think it would be a really good classroom activity, maybe a starter. So I'll send it out, but let's go ahead and continue with the rest of the presentation.
Perfect. Perfect. Sounds good. All right. So you will likely have an activity to work later at home, maybe, or at another class. So that's great. So, all right. So let's continue. And now let's look at space weather. Okay, so when you think of space weather, or when you hear the word space weather, maybe immediately we think of the weather we see outside, right? Again, it could be sunny, and usually when it's sunny, we say, "Oh, there's good weather." When it's raining, especially if it's pouring rain or if there's a storm, we usually say, "Oh, that's bad weather," right? And we try not to go out because we know, if the weather is too severe, like in a thunderstorm, for example. And we know currently at these right moments, in some places, even in this country, in our country, right, people are experiencing really bad weather, and we know it can be dangerous. But when we talk about space weather, it's similar, but actually, is the weather created by the sun, and this is the weather created outside our atmosphere. As I was explaining before, right, the magnetosphere is created by the magnetic field of the Earth that shields us from everything that comes from the sun. But even though it shields us most of the time, again, we just learned that if the magnetic field is pointing southward from the sun, and especially if it's a strong southward magnetic field, then this can create a geomagnetic storm. So now we're going to talk about, so what are some of these effects of space weather? Okay. So, all right, let's start with the nice weather, right? The good space weather. So just like regular weather, right? There's good weather and there's bad weather. So these pictures on the right might seem familiar to you because these are pictures of the aurora, or what we call the northern lights or the southern lights, depending on which hemisphere we are. And these are beautiful displays, right? That we can see, for example, this first picture here at the top left is a picture taken from space, right? You can see the Earth here, and you can see this beautiful green glowing color above the Earth in the atmosphere. And these other pictures are taken from the ground, actually. You can see in this one, you can even see the trees, right? So this picture was taken by someone on the ground looking up into the sky. And look at these beautiful colors, green colors and this violet reddish color that you can also see in this bottom right picture here. So um, all of these glowing skies represent one way of the good space weather manifests itself. And here I want to very quickly try to show you how this aurora is formed. So why do we have these glowing skies above us sometimes? So everything starts again with the sun. Hopefully you can see this animation. And this animation here is the sun. And then suddenly the sun just ejects a blob of mass of particles, right? And then all of these particles travel through the solar wind and they reach the Earth's magnetic field. You can see the magnetosphere there. And most likely, this solar wind was carrying a southward pointing magnetic field, so it created a geomagnetic storm, right? I'm going to play this again. And because the magnetic field of the sun was pointing southward, right, it reshaped the Earth's magnetic field. It reconnected with the Earth's magnetic field that you can see right there. It reconnects. And then all of these particles that you can see in yellow, right, they eventually will make it all the way towards down to the Earth, to the Earth's atmosphere. especially around the poles. You can see these glowing regions around the northern pole and the southern pole. So that's because all of these particles from the sun, when a storm occurs, they are able to reach inside the magnetosphere, and they follow these magnetic field lines, and they go all the way down to the atmosphere. And actually, I want to show you one more animation. And this animation, in this one, as opposed to the previous one, you will see again here the field lines in white, and here you will see what happens to every particle. Imagine you are a particle from the sun and you reach the Earth's magnetic field. And here you go. You have these yellow particles that, first came out from the sun. They traveled through the solar wind. They reached the magnetic field lines from the Earth. And now they follow these magnetic field lines down to the poles into the Earth's atmosphere. And what happens when they reach the atmosphere? They collide with the particles in the air, in the upper atmosphere. And when they collide, they excite these particles. And because they get the particles in the air, they get excited, they glow. And the colors you can see will depend on which particles in the atmosphere are excited by the solar wind incoming particles, right? So for example, you have oxygen atoms in the atmosphere, you have nitrogen atoms in the atmosphere, and depending which kind of particles in the air, in the atmosphere, are excited, that will determine the color of the aurora. Okay, so this is the good weather. This not just good weather, but actually space weather can be very beautiful, as you can see, because I've never seen this in person myself, but just looking at these pictures makes me really, really want to travel near the poles to be able to see this beautiful aurora. But space weather can also be bad, right? Just like regular weather. So when space weather is bad, space weather can be harmful, right? And can be harmful in a variety of ways. Solar activity, which generates space weather, can have significant impacts on communications, on satellites, on astronauts that are in outer space, and even can have an impact in animals as well. Okay, so we're going to take a look at some of these examples. So, for example, solar activity can interfere with cell phones, GPS, and other communications. So, did you know that in the atmosphere, within the atmosphere, there's one layer that's called the ionosphere. And this layer called the ionosphere, which is represented here, this darker band within the atmosphere, this ionosphere region of the atmosphere is electrically charged. So when we have a storm, for example, a geomagnetic storm, again, bad space weather, this ionospheric region is enhanced, is disturbed. And so this creates interference in the signals that we use, to use our phones. For example, when we want to go somewhere, we use our phones and we use our GPS, right, to indicate where we want to go, and then our cell phone app will tell us how we can get there, right, using our GPS. Those GPS signals also travel through this ionosphere region, and that's why if the ionosphere is disturbed, the signal from our GPS will also have inaccuracies. So the first example of a space weather effect is that communications can be disrupted, communications can be interfered with, and we can tell by the signal in our phones, the signal of GPS instruments, and other types of communications that use signals that travel through this region called the ionosphere. But not only communications can be affected, but satellites in outer space as well can be damaged or destroyed, right? If we have particularly more particles flowing in the solar wind, all of these particles can charge the satellites, meaning that they can be damaged or they can sometimes even be destroyed. If we keep going out, we know that not just in outer space, we not just find satellites, but actually sometimes we send people into outer space, right? And these are called astronauts. So astronauts, as they are in outer space as well, sometimes within this region called the magnetosphere, these astronauts can be threatened uh, by, again, the influx of the solar wind. When the solar wind is enhanced, uh, astronauts, they need to be very careful and try to stay inside the shuttles or inside the stations where they are in outer space. But not just astronauts, but also sometimes we have very high flying airplanes, and they can also be threatened by this solar activity. And as I mentioned before, even animals can be affected by space weather. And this is because some animals, like for example, some types of birds and bats, sea turtles, dolphins, whales, several types of animals, they use the Earth's magnetic field to orient themselves, to know which direction is north, which direction is south. And that's how they can know where they need to migrate to. So especially many of these animals, as they reach a season in the year when they migrate, their route of migration can be disrupted if, for example, a geomagnetic storm occurs. Why? Because as we saw, the solar wind during a geomagnetic storm will reshape, will affect, and um, yeah, just reshape, disturb the Earth's magnetic field. So these animals also can be disoriented due to these effects. But fortunately for us, uh, the near Earth space is being monitored constantly. So I previously mentioned satellites, right? And there are many satellites, many different types of satellites. For example, there are satellites that help us in our communications, right? For example, I mentioned the GPS that we use in our phones to get to the store or to go somewhere. We can just put the directions, and those satellites will help our phones locate themselves, and that's how we can know how to go somewhere. But there are other types of satellites that are constantly measuring what the solar wind is like, right? And here in this picture, again, you can see, hopefully this picture is more familiar to you now. We see the Earth here in the middle towards the right, surrounded by the magnetic field lines that create this bubble shaped like structure, which is the Earth's magnetosphere. And to the left, we have the sun, again, with the solar wind blowing away from the sun. And each of these little pictures here, drawings here, represents one satellite. And as you can tell, we have many satellites that are currently in outer space that are regularly monitoring the space weather. So each of these satellites, they carry a variety of instruments that are constantly measuring what the solar wind is like. So now we don't have to worry necessarily too much about space weather because fortunately we have these satellites that constantly are telling us what the solar wind is like. And they can tell us when an explosion from the sun, for example, is approaching the Earth. And so we can get warnings that a fast solar wind or a storm might be approaching our way so that we can take measures to prevent uh, any harmful effects. So, okay, so that's all I have for you. Thank you very much for your attention. Hopefully, you learned something new about the magnetosphere, about geomagnetic storms, and also space weather and how it affects us here on Earth. So, yeah, thank you. And I will, yeah, I think we have plenty of time for questions as well.
Wonderful. All right. I'm going to start with my own question
Mhm.
because when you were talking about, knowing if a storm is approaching, we can take action. What types of action might we take? So if the storm is coming Is there like certain things that we always do, or can you talk a little bit about that?
Yeah, great question. So if I go back here to some of my slides, right? For example, if we get a warning that some bad space weather might be approaching our way, for example, the first ones to be communicated likely are going to be astronauts, so they know they should not be outside, so they should go inside. For example, if they are currently servicing the International Space Station, for example, they will be told to go inside, right? For example, here, if we talk about satellites, all of these satellites, at least the newer satellites, they can operate in different modes. So again, when a warning is given that space weather might be approaching our way, these satellites, they know they can go into safe mode. So all their instruments will go into safe mode or sometimes they're even turned off to avoid harmful effects on satellites. And if we talk about, for example, communications, maybe here there's less things we can do. But for example, some instruments, again, just like in satellites, they can adjust for the change that the bad space weather will create in the ionosphere. They can account for those effects. Some of depending on which communication system we're talking about. But some of these instruments, they can adjust to account for those space weather effects. And these are just examples, right? But as you can see in this picture, I haven't talked about all the effects, but the, the, the basic idea is that all of the types of instruments or astronauts that we know can be affected by space weather, they can, take measures to prevent. If it's an instrument, change the mode of operation. If it's an astronaut, stay inside the space station. So things like this.
All right, very cool. Thank you. All right, heading over to the Q&A here. You talk about, like with the solar winds, you talk about particles. Are these physical particles like dust? Are these subatomic particles? Could you talk a little bit about that?
Yes, great question. I didn't go into details about these particles, but these are real particles. Mostly, we find very energetic electrons and ions. Electrons are the particles with negative charge, and ions are particles with positive charge. So we have both types of particles flowing in the solar wind, electrons and ions. And ions there are different species of ions, different types of ions. The most common ones are hydrogen ions, which are the most abundant in the sun and elsewhere. But there are also some other types of ions, like helium ions and some other heavier ions, we call them. But yeah, these are real particles, mostly electrons and ions.
All right, great. All right. Do solar winds or flares have an impact on the temperature of Earth during that time?
On the temperature of the Earth, good question. So this is something I don't study directly, but the effects of solar wind, like of sun explosions in the sun, like flares, or bad solar weather or space weather, should not necessarily affect the temperature, like on the ground, the temperature we measure here, because again, we have different layers of the atmosphere, and so these types of events really the all the effects that they will create are in some way related to electromagnetic effects. So they create currents, they disturb the magnetic field of the Earth. So the category or the type of effects that are created are electric and magnetic, but not necessarily the temperature. No. So the temperature on the Earth, in the ground, especially, should not be affected by these types of space weather events.
What is the biggest solar storm to hit Earth?
What was the biggest?
Yes.
Okay, so there's a very famous storm that occurred in the 1800s, 1850 something, if I remember correctly. And this event is called the Carrington event, and you can tell that this happened, over a century ago, like many years ago. And but even though it happened many years ago, we have some reports uh, of the effects, again, the space weather effects that were seen by people during this event. And this is how we know and how we estimate that most likely this is the largest storm recorded, at least in our history. We don't know the specifics of this event, again, because it happened in the 1800s, but by the reports that we currently have by some scientists, some historians, we believe this was by far probably the strongest storm that hit the Earth. But as a side note, May of this year, we had the largest storm in over 20 years. So that was also a very large storm that hit the Earth May of this year.
Oh, all right. How often do these storms happen?
Very good question. So these storms happen, it depends. Sometimes we can have one or two in a month. It's very unlikely that we will have more than one or two a month. But sometimes, when the sun is very quiet, we can have, several months without any storms. But basically, yeah, maybe just a couple per month uh, when the sun is most active. But when the sun is quiet, we can go, several months without a storm.
All right. Um, do humans have any sort of impact on the magnetosphere?
Hmm. Another good question. Another good question that's slightly outside of my field, but um, but I think it's very unlikely, because if I can go very quickly back to my first slide when we talked about the Earth's magnetic field, right? The whole um, the whole mechanism that gives rise to Earth's magnetosphere is the fact that the Earth is a giant magnet, right? And the Earth is a giant magnet. We believe, scientists believe that it's because at the center of the Earth, there has to be, or there must be, some liquid metal near the core of the Earth. So that's what's creating the Earth's magnetic field. So, this is something that would be very hard for us here and in the surface of the Earth to affect. So I think my best attempt to an answer to that question would be that it is very unlikely that we humans can affect, this region called the magnetosphere, can affect the Earth's magnetic field and all the interplay between this region and the solar wind.
All right, thank you.
Mhm.
All right. How strong is the solar wind compared to wind on Earth?
Ooh, how strong is the solar wind compared to the wind on Earth? Yeah, much faster, much faster. Actually, activity number two that I had planned is directly related to how fast the solar wind is blowing, is traveling. So yeah, maybe this will spark some interest in some of you to do activity number two. But for example, when we talk about the speed of wind here at the ground, we're talking about what, like maybe, I don't know, like 30, 50, 60 miles per hour, right? The solar wind speed, we're talking about hundreds of kilometers per second. So this is significantly uh, faster than wind on the ground.
All right. Wow. I wouldn't want to be out in the out in space when that blows.
Yeah, yeah, certainly not.
All right. So how did you know that you wanted to study space weather, and how can, students now, how can they help prepare if they're interested in this field?
Mm, yeah, good question. So when I was in middle school, for sure, I didn't know I wanted to study this. When I was in middle school, I think all I knew was I loved math because that was my first love was math. I loved math, and when I took physics for the first time, uh, I fell in love with physics even more because it was like using math, but to calculate all sorts of cool stuff like temperatures and distances and things that you can, relate to in everyday life. So I fell in love with physics and I always had a fascination for space. So eventually, when I went to college, I connected both things. I connected my love for physics and my curiosity for space, and that I think took me to follow this path of studying space physics. And so, if some of you are interested in this, I would say maybe one thing to do is, well, get better at math because we use a lot of math in this field. Also, I don't know if you have taken physics to some degree at some level, but physics, of course, is very important in this field. And maybe one other suggestion or advice would be to maybe just go take full advantage of your teachers, your professors. Maybe ask them for activities like the ones we've done here and the ones that you probably do in class. Just maybe get more involved with extracurricular activities that where you can learn more and develop those skills.
All right. Thank you. All right. There's another question here that may be outside of your area of expertise, but I'm gonna read it anyway. With the solar max happening now, what tips can you give about aurora chasing?
Ooh, yeah, great question. Which implies that you know what solar max and solar minimum are. And you're exactly right. We're approaching the time when the sun is most active, right? And for those that are not familiar with this, um, the sun's magnetic field like going back to this picture, right? Here we have one pole and the opposite pole, right? And this is, of course, for the Earth. And these two poles, in the case of the Earth, they are moving, they are drifting, but very slowly. We will not notice a big difference in our lifetime. But in the case of the sun's magnetic poles, they flip every 11 years. So every 11 years, the magnetic field of the sun changes completely. So that creates what we call the solar cycle. So the solar cycle lasts 11 years. And during those 11 years, we have a period when the solar activity is at its maximum and then it's at its minimum, right? And then every 11 years, we repeat that. So right now we're approaching this period called the solar maximum, which means the sun is more active. So we have, it's more likely that we have explosions, geomagnetic storms, and therefore aurora as well. So aurora, going back to the question, is kind of difficult to predict. Of course, the closer we are to the poles, both the northern and the southern poles, the more likely we are to see them. But fortunately, there are several ways you can monitor how likely it is the aurora to be seen in different regions. And one that comes to mind is Aurorasaurus. There is an actually citizen scientist-driven platform called Aurorasaurus, and you can just Google it and you'll immediately find their website. And they do a great job helping people know when and where the aurora might be seen. So I would recommend checking that website out. Hmm.
All right. Yes. Aurorasaurus is actually one of the other teams. We're a NASA-funded project. They are one of the teams that we work with. So I'm going to go ahead
Hmm.
and glad you mentioned them. I'm going to go ahead and put their link in the chat here. for those of you who might be interested.
Yeah.
All right, and we just have a couple minutes left. I'm going to wrap it up with one question, and that is like what tools or techniques do scientists use to study the magnetosphere, and are there any like NASA missions that are currently part of that?
Great question. This is exactly what I do. So I'm happy to answer that question. So let me again move through these slides towards the end of this presentation. Okay, so let me quickly answer this question. Basically, there are three ways we can study space weather, the magnetosphere, and this broader field that we call space physics. Okay. So I'm a space physicist, and space physicists we study this region of space which we call the near Earth space, right? Within which is the magnetosphere. And there's basically three ways we can study the magnetosphere. One is theory. There's a lot of scientists that are theorists, and they, spend a lot of time in their desks, in their labs, just, playing with the equations and predicting what new phenomena can occur, what, new phenomena should occur in different regions of the near Earth space, right? So we have theorists that, have to be very knowledgeable with the physics, with the math, with the equations, and they are the ones that are going to make predictions. Then we have what we call instrumentalists or data analysis people. And these are the people that are going to both create instruments to be flown in all of these satellites that you can see in this picture here, and the people that are going to analyze the data, the measurements taken by those instruments, right? So we take measurements, right? Measurements are very, very needed to study this region. And unfortunately, this region is so far from the Earth, right, that we need satellites to study this region. And that's why you see all these satellites in this picture, right? That's how we uh, can measure things, right? So we have the instrumentalists and the data analysts. And then finally, the third way we can study this region is through computer simulations. So there are people who, go down this route and they take all of these equations that the theorists have come up with, and they create computer codes, computer models that can create simulations like the ones I have shown you. I've shown you several simulations actually. Let me go back. This one, for example. This is a computer simulation, right? So this is the product of work of space physicists that devote themselves to creating computer models. And these are very helpful because you see, we can get an idea of what space looks like. And we are able to predict as well, using these computer models, how, for example, a solar storm can affect us on the Earth, right? So these computer models are very, very useful. And I particularly do the last two ways. I use the last two methods, right? I do data analysis, and I also help with computer models. And here at NASA, you will find the three kinds: the theorists, the instrumentalists slash data analysts, and also a lot of computer modelers. So these are three ways we can study um, this space weather and space physics.
All right, wonderful. And we are at time, so I'm going to just say thank you so much for taking the time today to share your expertise with us. It was very illuminating. I feel like I know a lot more about the Earth's magnetic field, and I think our audience does as well. So thank you. And I'd
Sure.
also like to thank everyone who joined us today. I will be sending out the recording and some of those links as well. So please do look out for that. And with that, I'm going to go ahead and stop recording and just say thank you again for everyone for joining us. And we hope you'll join us for the next talk, which will be next Thursday. And that is specifically on the aurora. And we have another one the following Wednesday that is on computational modeling of space weather. So both of those are available at the same registration link that you used for this one. So we hope you'll join us. Thank you so much.